In the world of science, we're all looking for clear, solid answers, right? But what if I told you there's a kind of hidden saboteur, a statistical ghost that's haunting research, creating all this confusion, and honestly, leading scientists down the wrong path? Well, today, we are going to go on a little investigation to unmask a culprit that complicates thousands of studies, often without anyone even realizing it's there.
So, here's our game plan. First, we're going to tackle the core puzzle itself. Then we'll meet the usual suspects that researchers always look for. After that, we unmask our hidden culprit, a little something called IRR. We'll see how it was caught red-handed in a simulation, look at the hard evidence, and finally talk about the ripple effect this has on all of us.
Okay, let's dive right in. Part 1, the validity puzzle. You've probably seen this before, right? A headline pops up claiming some new hiring test is a game changer, and then a year later, another study says it's totally useless. This happens constantly. Scientists are looking at the exact same relationship, say a pre-employment test and how well someone does their job, and they end up with this messy, confusing pile of conflicting results. This variation, that's the mystery we need to solve. Now, to sort through this mess, researchers came up with a really powerful tool called Validity Generalization. You can think of it like creating a super study. It takes the results from dozens, sometimes hundreds of individual studies and blends them all together. The whole point is to wash out the random noise and find the real, underlying truth. And this isn't some niche thing. It's a huge deal in fields like psychology and management. So, when researchers use this tool, their first job is to figure out all the known reasons why study results might be all over the place. So let's meet the usual suspects. These are the known troublemakers, the ones everyone knows about. Scientists have a list of 10 of these statistical artifacts. Things like, just random chance because you had a small sample, or maybe your measurement tools weren't super reliable, or even just typos in the data. They've got formulas to correct for the noise these things create. But, and this is where our mystery really starts, even after they've corrected for all 10 of those usual suspects, researchers can usually only explain about 80, maybe 90% of the variation they see. There's always this chunk left over, a stubborn 10 to 20% of what they call unexplained variance. It's like a statistical black box, a ghost in the machine. And for years, scientists have been asking, what is causing that? And that brings us to the prime suspect in our investigation, a factor that might just be the key to that whole missing piece of the puzzle. It's a really sneaky phenomenon called indirect range restriction, or IRR for short. Now, to really get our culprit, you need to know it has two forms. First, there's direct range restriction. That one's obvious. It's like a farmer who intentionally picks only the biggest apples to study. But the one we're after, indirect range restriction, is way sneakier. It's unintentional. It's like that same farmer picks only the sweetest apples, but in doing that, he accidentally ends up with a group that's mostly red, which totally messes up any later study on apple color. Let's see how this plays out for real.
Okay, check out this classic hiring scenario. A company uses a cognitive test, we'll call it Test Z, to hire people. Makes sense, right? Only the people who score well get offered the job. So far, so good. But now, a year later, the company wants to try out a new personality test, Test X, to see if it predicts job performance, we'll call Y. They give Test X to their current employees. Do you see the problem here? This isn't a random group of people anymore. It's a pre-filtered group of high scores from that first test. And since that initial cognitive test is probably related to both personality and performance, the relationships you're seeing now are all distorted. The data is compromised before you even start. So, to put it simply, indirect range restriction is what happens when you filter a group based on one thing and it unintentionally squeezes the data for other related things. It's kind of like trying to judge the entire rainbow by only looking at shades of blue. You're just not getting the whole picture, and any conclusion you come to is going to be skewed. And get this isn't some new, obscure idea we just cooked up. The famous psychologist R.L. Thorndike was warning about this way back in 1949. He called it, by far, the most common and most important problem for this type of research. And yet, even though we've known about it for over half a century, its exact effect on that unexplained variance has been a total mystery. Well, until now. So how in the world do you catch a statistical ghost? Well, the researchers basically built a digital laboratory to drag it out of the shadows and finally measure its impact. They used this incredibly powerful technique called a Monte Carlo simulation. The best way to think about it is like a flight simulator, but for statistics. It lets researchers create a perfect, known universe inside a computer where they know the absolute truth about everything. Then they can run the same experiment thousands, even millions of times, just tweaking little things here and there to see what happens. It is the ultimate way to stress test a statistical problem. So inside this virtual lab, the researchers played with everything. They cranked the severity of IRR all the way up and dialed it all the way down. They tested different sample sizes to reflect what real-world studies look like, and they systematically changed the true strength of the relationships between all the variables. They did all this just to make sure their experiment was as close to the messy reality of research as possible.
And we're not talking about just a few scenarios here. They ran an absolutely astonishing 19,422 unique combinations of these conditions. And for every single one of those conditions, they generated 5,000 samples. You do the math. That's nearly 100 million virtual studies. This was a massive, exhaustive investigation designed to leave absolutely no stone unturned. Okay, so after running one of the most comprehensive simulations ever done on this topic, the researchers had a mountain of data to sift through, and what they found finally confirmed the true identity and the impact of our hidden culprit. And this is the smoking gun. It turns out the standard formulas that researchers use to guess the amount of random noise, what they call sampling error, already tend to underestimate it a bit. But when indirect range restriction shows up, it makes things so much worse. The real amount of random error becomes significantly larger than the formula says it should be. The ghost was real. IRR was actively pumping extra, unaccounted for noise into the data. So, what was the damage? How much extra noise are we talking about? The simulation showed that under certain conditions, IRR inflates that random statistical noise by as much as 8.5%. Now, that might not sound like a huge number, but in the world of statistics, trust me, that is a massive effect. It can be the difference between a finding being celebrated as a breakthrough or just dismissed as random chance. It can completely flip a study's conclusion on its head. The researchers also found this really critical pattern. The damage from IRR isn't the same everywhere. It hits the hardest in studies with smaller sample sizes, say around 60 people, and its effect gets smaller as the samples get bigger. This is a huge deal because so many real-world studies, especially in fields like hiring, are working with those smaller, more vulnerable group sizes. You know, a small group is already susceptible to weird random results. IRR just pours gasoline on that fire. Okay, so we've unmasked the culprit, we've seen the evidence from this incredible simulation showdown, but what does it all mean in the real world? Because this isn't just some quirky statistical detail, it has some pretty profound ripple effects. Here's why this matters to all of us. When researchers see that extra 8.5% of unexplained weirdness, they don't think, oh, that's just IRR noise, they think it's a real discovery. They might conclude that a hiring test works for one group of people but not for another, a conclusion based entirely on a statistical ghost. This wastes tons of time and research money chasing dead ends, and worse, it means that real-world decisions that affect people's careers could be based on fundamentally flawed data. It all points to one clear call to action for scientists. You have to report every single detail about how your participants were selected. It's the only way we can finally account for this hidden culprit. And all of this leaves us with one last, kind of spooky question. This investigation unmasked one hidden culprit that makes research more uncertain. But it really makes you wonder, doesn't it? As our tools get better, as our statistical forensics improve, how many other things we think are real discoveries, how many of those headlines you see, are actually just statistical ghosts, still out there, waiting to be found?